I'm gonna start recording from Zoom so that we at least have the rest of it there. So I think it's recording from my iPad because it was doing the screen share, so I should be able to grab that recording for later. Okay, so that was kind of interesting. So notice the pieces that we had to put together on this. We had to take that sort of density of the chain kind of thing, not really a density, but how many pounds, its weight per foot. So weight per unit of length. And then we looked at the work done moving that kth piece. That's going to become essential. We're going to do the same thing in lots of problems. And then once we multiplied those guys together, we had to multiply by the distance each piece had to move, because that's what actually gives us work. So we had the weight of that piece times its distance moved. Once we had that expression, we were in good shape to integrate. So if you think about it, we put all of the details in here, but what we really needed, we could have probably skipped. You know, if you didn't write this step down, that would be okay, but you really need this because that's what tells you how your integral gets set up. Notice the 2.5 is there, the 10 minus 2y is there, the dy is there, and that's what built the integral we wanted in order to calculate the work done. All right, so let's try at least one more.
Did you just wait? We go back up for a second. Did you just write the WK there equals?
I wrote that a while ago.
Oh, okay.
That was there before.
Oh, okay. I was just wondering. I didn't have it on my paper, so I was just wondering.
Okay. Okay. So we're going to do a similar one, but it's not a chain. It is a tank of water. So we've got this water reservoir, and it's 20 feet in diameter, and it's cylindrical. So that's kind of nice. You're just thinking big cylindrical water tank, not necessarily drawn to scale. It's 20 feet in diameter across the top. 20 feet across the top, and definitely not drawn to scale because it's only 15 feet deep. So I drew this taller than I needed to, 15 feet deep. It's filled to a depth of 10 feet. So somewhere here at the 10-foot level is how much stuff, a water reservoir, how much water I have in here. So let's make that blue. Water goes up to that level. If it's filled to a depth of 10 feet, how much work is required to pump all of the water to the top of the reservoir? So in other words, you've got a pump in here. It's got to get some work done. And the work that's done is that all of the water is moved up here to the top. So think of having it come to the top and shoot out onto the ground if this thing is buried. Or think of it coming to the top and going somewhere after that. But I only want the work that is done in getting it up to the top, no further. So we just have to get it to the top of the reservoir. How much work did we do in doing that? So this is where the physicists and the mathematicians will probably disagree a little bit. One could say that all of the water actually had to get pumped from the bottom of the tank because it goes down there to get to the pump and then shoots its way up through something, you know, hose, some kind of tubing, whatever. But we're going to look at it as sort of the net work that's done. In other words, the water that is initially at the top, at the 10-foot level, doesn't have to move as far as the water that's initially at the bottom, at the 0-foot level. So if I draw my coordinate system again, the bottom of this thing is 0 feet, the top is the 15-foot level, 10 foot is of interest because it's part way up. Okay, so what do we need to know? So this isn't a linear thing like that chain link. This is just a bunch of water. Do we know or can we figure out how dense water is? Notice our units are not as nice here because we're dealing with English units. So we need to know how many pounds, how much this water weighs. Does anybody know, or can you find the weight density of water in English units? In other words, how many pounds per cubic foot of water? This is one of those numbers that's right off the top of your, at the top of your head, right? Weight density of water. Come on, you guys have Google. You can go find it. I think it's 62.5, but it might be 62.4. In pounds per cubic foot. Here we go, 62.4. I was off by 0.1. 62.4 pounds per cubic foot. So every cubic foot of water that you have in here weighs 62.4 pounds. Now, we can't just assume that it all has to move, say 10 or 15 feet, because it doesn't. Remember, the stuff at the top only moves 5 feet. The stuff at the bottom moves 15 feet, and so on. So we're going to have to sort of break this up the way we did the last time. And we're going to break it up by slicing, just like we did with our volumes. If I slice across this cylindrical tank, what's the shape of every little slice of water? I know that sounds really strange. Slices of water. So if I take a slicer like right here.
It would just be a circle, wouldn't it?
It would just be a circle. All right, so let's think about how we get the weight of a little disc of water. Well, we need to know how big that circle is, its area, and then we need to know how thick it is, but its thickness, just like before with the chain problem, its thickness is going to be a little dy. So break this up like before. We're going to do first, I'm going to go all the way in pieces. Area of one piece. And they may or may not change. In this case, since my picture is a cylinder, isn't the area of every one of these the same? No matter where I draw that little slice of water, the area is just pi times radius squared. And in this problem, the radius is always how many feet? 10 feet? So 100 pi square feet. The thickness of each piece is our little delta y or dy. And to get our volume, what do we do with area and thickness? Now we're going to multiply those together. So we'll have our 100 pi times our dy, probably some k, times dy sub k. And now our units are cubic feet. I like to keep track of units along the way, because if I do that, then I can make sure that what I'm really adding at the end, what I'm really adding up together is work, because that's what I want. So I want to make sure that I'm working in foot-pounds when I'm done. Okay, I've got the volume of that piece. And up above, remember I had my weight density of water. So my weight for my kth piece is 100 pi dy cubic feet times 62.4 pounds per cubic feet. And the cubic feet cancel and I get pounds. So I've got 6240 times pi times dy. And I'm in pounds, so I'm good. I really do have the weight of that sort of slice of water. The only other piece I need is how far it moves. And this is probably the last piece that people tend to end up forgetting. How far does water at level Y move? All right, well, let's write in some examples over here. If we're down here at the 0 foot level, how far does it have to move?
15.
15. If we're at the 3 foot level, we're not going to do these in ones. How far does it have to move? 12. If we're at the 7 foot level, we move how far? 8. Okay, if you're at the Y foot level, how far does it have to move? Well, let's see, this plus this always adds up to 15. So it's 15 minus Y in feet. 15 minus Y feet. So the work for the kth piece is my weight, 6240 pi, times the distance it moves, 15, minus Y, and don't forget my dy. And so there's my integration piece. I'm going to integrate 6240 pi times 15 minus Y dy. From where to where? What should my limits be?
5 to 15.
Okay, look at your water. Where is my water in my picture? My water is down here at the bottom, up to here. So that's where my water is.
0 to 10.
0 to 10. If you drew your coordinate system the opposite way, in other words, if you put 0 at the top and 15 at the bottom, which is completely legitimate, then your limits would be 5 to 15, but your description for this expression, the 15 minus Y, would be different. So in our setup, 0 to 15. So I am going to open Mathematica. I'm feeling lazy. Where? No, there we go.
Wait, I thought you said that limits was the 10, not the 15.
I did say 10 and I wrote 15. Thank you very much. So let's
Okay.
erase that. Thank you. Let's erase that 15 and fix that subscript, and that should definitely be a 10. Okay, so integral from 0 to 10, and I am going to go ahead and seal the screen share.
You want it in terms of pi?
Yeah, it's going to depend. Generally, I don't care.
Okay.
So you could multiply it all out and give me an approximate answer. Just be careful with
Decimals.
be careful with Alta so that you're giving them what they want. So if they ask you for an answer, you know, to round it to 2 decimal places or with 3 significant digits or whatever they ask for, just give them that. If they say give the exact answer, then you're going to want it in terms of pi.
Okay.
So we want the integral of 6240, and the easiest way to get pi in Mathematica is just pi with a capital P times 15 minus y. And then y goes from 0 to 10. And notice that Mathematica gave me the answer in terms of pi. Did you guys agree with me there? 624,000 pi. And my units would be, oops,
Yeah, I agree.
foot-pounds. And we could, you know, you can
Multiplied out is 1,960,353.816.
what did that just do? Oh, it just, so I'm going to kill that. Delete. It uses a generic number instead, and then a numerical value. So is that what you got? 1.96 million?
Yeah. Yeah, that's what I got.
1.96 times 10 to the 6 foot-pounds. Okay. So not too bad. All right, we are not going to do number 4 right now. I'm going to save that one for later. I just want to do a setup on one more that's similar to the one we just did, but not precisely the same. So I'm going to scooch this down to the bottom. The only change I'm going to make, and I know I need to, let's stop my share there and go back and share here again.
It was foot-pounds, right?
Foot-pounds. Yep. All right. So we should be back here. So same problem as before. The only difference, I'm gonna do a little change on this. My reservoir isn't a cylinder anymore. It's conical. So the piece that's going to change, so it's still 0 to 15 and still 10 feet of water in this thing. What piece is going to change in all that work we just did? I'm sorry, I can't hear you.
The spot where the water's at?
The spot where it's at, I don't think that, no, it's still 0 to 10.
Oh.
I don't think that changes.
The diameter?
Yeah, the diameter changes or the radius changes, right? Remember, for each piece, we used area equals pi r squared. And we were able to assume that the radius was always that 10-foot radius that we have at the top. But now we don't have that because the radius isn't always 10 feet. At the very top of this thing, it's 10 feet. Right here at the 10-foot level, it's something less than 10 feet. Down here at the 0-foot level, it's 0. So what I need to know is, how does the radius compare to the y level that I'm sitting at? So if I'm at level y, what's my radius?
10.
And the way I'm going to do this is by remembering something from way back in geometry. And it's similar triangles. Remember how similar triangles had sides in proportion to each other? So the y value compared to the radius should be the same as the y value compared to the radius anywhere. So for example, this y and this r. But even better than that, it should be the same as the ratio of this y to this r, and we know that radius. So everywhere on this cone, the y value compared to the radius is always, let's see, the purple has a y value of 15 over a radius of 10. So 10y equals 15r, and r equals 10y over 15, or a little bit simpler, 2/3 y. So the only difference in this problem and the last one is that instead of area having a 10 squared for this r, it's pi times 2y over 3 squared. Or area is 4 pi y squared over 9. Everything else is going to come out the same. So the distance moved piece is still going to be 15 minus y. My limits are still going to be 0 to 10. My weight density of water, still 62.4 pounds per cubic foot. So my integral looks like this: 62.4 pounds per cubic foot times my area piece times my dy times my distance moved, which was 15 minus y, and y goes from 0 to 10. And that should do the trick. Okay, I think we are really at a good spot for today. I'm not going to do any more examples. I do want to remind you of one thing. Be careful when you're working in metric units. In metric units, students usually remember this. What's the mass density of water? What do you remember the nice thing about metric units and density of water?
Isn't it gram per centimeter?
Gram per centimeter. 1 gram per, I think you mean cubic centimeter.
Yeah, I did, sorry.
Right, okay. So we're going to convert that to standard units, which will be newtons per cubic, or not newtons, kilograms per cubic meter. Okay, so how do we get from centimeters to meters? Well, there are 100, right? So 100 centimeters per every meter, but I have to cube that to get to cubic. So that's going to give me grams per cubic meter. And then I remember that there is 1 kilogram for every 1,000 grams. And now my grams will cancel, my centimeters will cancel, and I'll get kilograms per cubic meter for my units. Oops. Meter cubed. And I want to get rid of that equal sign, so we'll put it over here. Equals. What's the number there? So I've got 100 cubed, that's 1 million. 1 million. And I've got 1,000 in the denominator. And 1 million divided by 1,000 is 1,000. So that mass density of water is 1 gram per cubic centimeter, but that translates to 1,000 kilograms per cubic meter. Now, this is where the English system and the metric system are a little bit different. The metric system generally deals in mass units, whereas the English system deals in weight units. So we look at pounds in the US, whereas other places all measure their weight, it's really their mass, in kilograms, right? In order to turn that kilograms per cubic meter into a force picture or a weight picture, we still have to measure by multiply by the acceleration due to gravity to turn this into a force. Remember, force is mass times acceleration. So mass density of water is 1,000 kilograms per cubic meter. Weight density is that mass density, 1,000 kilograms per cubic meter, multiplied by the acceleration due to gravity, 9.8 meters per second squared. And you can do all sorts of things to manipulate units. So, but your weight density is going to be, and that this will give you newtons, 9,800 newtons per cubic meter. Now, the one thing to be careful of is just to make sure that you're using both of those pieces. So most of the time they'll put these in separately. So your 1,000, your 1,000 times your 9.8. If you put them in together, you're fine. Just make sure you get both of those dimensions in there. So if you're working in metric, you do have to take that 1,000 and multiply it by the 9.8. In US units, you don't, because it's already factored into that weight density.
Is that 9.8 or 9 times 8?
That is 9.8. That's the acceleration due to gravity. Metric units, right? 9.81. Use 9.8. Okay. The reason for splitting these out would be that if you had something other than water, you might have a different mass density here. And then you'd still multiply by the 9.8. All right. You guys have any questions? All right, I am gonna put
I have
this
a question.
recording. I want to say one thing before I end up forgetting. I'll put the recording together. Remember, the Zoom recording is not going to have everything. I will try to retrieve what I can from. I don't know if it recorded it or not.
I have a quick question.
Probably didn't record it, but I can still. What I'll do is I will include the work that I did for anybody who's looking back later from that practice problems worksheet. So all of this will be, I'll just put that up in notes.
Hey Phoebe, that last question we did, that was not the last one. The last one we worked out. The second to last one I guess we worked out.
With the cylinder, okay?
Yeah, that was foot pounds, right?
That was foot pounds. Oh,
foot times pounds, right?
Oh, yeah. Let me see, 20 feet. You are correct. Yes, that was. Yeah, and my note about mass density was really just meant to be a separate thing, just so that if you're working in metric, you'd know what factor to use there instead of the 62.4.
Thank you.
And oh, wait, let me fix one thing first because I see an error. This should be pounds per cubic foot, not pounds per foot. I think I said it right back there, but I may not have. In any event, that needs to be a cubic foot. Okay, so I will save this and I will post this up in, I will post this worksheet from today up in eLearning as well, just so if anybody missed or if you want to look back at something in the notes, you can go back and find it.
So that answer for that one would be pounds per cubic foot or feet cubed, right?
The answer?
Yeah, that's
So
what I meant.
remember, you're multiplying all these units together, and I didn't write down the rest of my units, so let's pay attention. So we have 62.4 pounds per cubic foot.
Mhm.
Then y is going to be in feet, so that's going to be times feet squared. And y is going to be in feet again, more feet. And let's see, what else have I got? dy is a change in y, so that's so it looks like we have too many feet, but if we think about how these cancel, we don't. We're in good shape. Feet cubed cancel with feet squared and feet. So we're still left with a foot over there. And we've got pounds. Pounds times feet. Our answer is in some number of foot pounds. Because remember, we were calculating the work done. So our answer needs to be in units of work, not in units of something else.
And always foot pounds usually.
If you're working in the English system, generally you probably work in foot pounds. If you're talking about something where you're not doing very much work, it might be inch pounds or inch ounces. I mean, theoretically, it could be any multiplier of a distance and a weight. So foot pounds, inch ounces, mile tons. I'm just being crazy. Okay, other questions? All right, I am going to end this because I got class in 10. So I will see you guys all next week. I think that's a significant number of applications for you to look at. So that should be pretty good. All right.
Thank you.
Thank you.
Yep, you're welcome. You have a good weekend too, everybody.
Have a good one. Bye.